State what is meant by specific latent heat. Hey, it's the L. Latent heat refers to the L in the equation. So if you like, Miss, I don't know what's the equation. What was the definition? Remember Q equals to ML. ML is not mobile legends, it's mass times latent heat. So if you say L, that will be heat supplied to a certain mass. To do what? Melting. All right, melting, phase change. This one got no change in temperature, no data. Phase change. So the very first one, you can say that this is, what's Q? Thermal energy. So we say the thermal energy divided by M. The best way to say is per unit mass. How much energy need to convert 1 kg of substance? Okay, thermal energy per unit mass. You can say per unit mass or 1 kg of mass to change the state of a substance from solid to liquid, liquid to gas, change. But there's one more thing very important here. Here we say change state. We only want to look at the part where there's no change in temperature. So we must also specify here without a change in temperature. Without a change in temperature. Oh, but miss, this part is not in the equation. Yeah lah. There is no data here, right? So you must say no data. So the first part is thermal energy or energy per unit mass to change state. Is the first idea. Without a change in temperature. This is the second idea. So let's call this a B1 and a B1. You can say without change in temperature or at constant temperature. Constant temp. Yeah, that works. Okay. Okay, so far, let's go and see the setup. Okay, we are boiling water now. A beaker of boiling water is placed on the pan of unbalance as illustrated below. Okay, so your container of water on this balance. What is a balance? If you forgot what balance is, it's those things where you measure how heavy things are. And over here, you will see a screen that tell you, don't know, 200 gram or something like that. And it will keep changing lah. So the water is maintained at boiling point. So no change in temperature. Boiling point is 100 Celsius. Fixed. No change in temperature. But then the change in mass in 300 seconds over a certain time is determined for two different power of the heater. So actually, if you do this experiment, you see it start to bubble. Oh, forgot the heater. You see this circuit. Circuit give energy to the heater. Heater give energy to the water. Start to get hot. Basically, it's a nice big resistor. So as the water get hotter and hotter, the bubbles start to appear. It start to boil. Blah, 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 blah. Steam come out. Everything come out. Okay, boiling already. And as you boil off the water, this scale will get lighter and lighter. Less water, boil, gone already. So quick note about the heater, heat supply. What are some equations for electrical energy? Can you recall any equations for electric energy? So for electricity, you need to remember it's very useful for this chapter because we'll be using a lot of heaters like this. There will be some basic electricity. So one is for energy, okay, electrical energy, E equals to V, voltage, okay, the V here, current, I, measured by this ammeter, so current flowing, times the time that your heater is on. Is energy. There is also one more equation, power of heater, electrical power. This will be, power is what? Oh, power is defined as rate of energy change or energy transfer over time. So you take this whole thing, Divide by time, you get P equals to IV. Or the other variations will be V square over R or I square R. All the variations of power. Okay, so must remember a bit your electricity. Firstly, E equals energy, VIT. Power, all this stuff. Let's give it a nice highlighter here and here. I remember the main one can already lah. Alright. So we're going to use these equations later to do some calculation. But first, let's go and see what they want us to explain first. Okay, so they have two reading. At one moment, they use some voltage, some ammeter, so the heater is some power. Then you see this much of mass disappear already. Psst, evaporated. Evaporated and condensed somewhere else. Then you change to higher voltage, higher ammeter. Ooh, even more mass evaporates. A lot of steam come out, gone. Bye-bye. Okay, interesting. We'll use that calculation later. Energy is supplied continuously by the heater. State where in this experiment external work is done. Now this one is a bit of a strange idea. Why suddenly got work done one? It's partially related to another chapter that we are learning after this. But you can also remember last time how we calculate work done by gas. There is a work done formula, which is pressure of gas times a change in volume. In other words, the gas or some substance is pushing against something else, doing work. Like how you push a box, you do work. So here you think of work done, external. So we think of how is this related to external? Where is work done? This one I'll give you all a heads up on how to do this one since we haven't fully discussed about this yet in the theory. But here you can think about it this way. In this container, you have water molecules inside the water. H2O, very cute one. Got two like Mickey Mouse like that. Two small thing, one big one. So got lots of water molecules inside here. And in the air, there is already there's already air molecules. I don't know what they are. They could be nitrogen, oxygen, whichever. They're already there. Everything is nice and balanced. Suddenly, when you hit that boiling point, some of these H2O will start to escape. They come out. Lots of them come out actually. So they're like, "Whoa, escape," because become gas ready, you are free, liberated, push out. But there's already gas molecules out there. Your volume is expanding, but there's already people out there. So actually, this water or this water gas is now doing work against the atmosphere. It's pushing out. It's like, excuse me, we want to come out of the water into the air now. So it's doing work against the atmosphere, atmospheric pressure. So here we can say work done against. They ask you where ma. So here, here work done against the atmosphere. So if your air outside don't have a lot of particle, very easy to boil water. Short while, everybody can come out already because no need to do so much work to get out. So work done against, or you could say work done on the atmosphere. Okay, or you could think of it as your water is becoming gas and the whole volume is getting bigger and bigger. So it push and push and push against the atmosphere. Okay, next part. Internal energy increases. Well, we talked about internal energy just now. Internal energy has two parts, KE and PE. You look at this setup very carefully. What is increasing? Heater is giving energy to water. Is it kinetic energy increasing or potential energy increasing? Are any of these increasing? And why do you say that? KE increase? PE increase? Alright, so if you're thinking like, oh, what's KE and PE? KE is related to temperature. Remember, you vibrate a lot, you move a lot, you are very excited, you got a lot of temperature. PE is how far apart are we? We're very far apart, our PE is very high. Phase change. So here there is no increase in KE. Temperature is constant, so PE is increasing. Huh. If PE increasing means internal energy increase lor. Where? In the water. So we tell a story here. As water is boiling and changes its state, or you can say changes from liquid to gas, liquid to gas, the potential energy of the molecules increase. Because they're getting further and further apart. Gas particle very far away. Right? So what does that mean for internal energy? So internal energy of water increases. Energy of water increases. There we go. So they ask you where internal energy increase, you say then the water lor. So this one, internal energy of water increases. This is a key idea, but sadly no marks though, because they already say increases. So if you say increases again, it's they want you to explain, not state and explain. So we need to explain this. So how to explain internal energy increase? Because water boil. The water is boiling, change state. So this one, M1. So here's talking about a change of phase or state. So what does that mean? Oh, PE increase. They're further apart. PE increase means got internal energy increase. Okay, that's how you can link these three ideas together. So 1, 2, 3. Okay, correct. All right, last one for this question. This one I'm going to give you all some time to try it out. Just try and error, some ideas. So now we have come to the calculation part. Use the data from figure 2.2, this nice table. How much mass is gone in 300 seconds. Determine the specific latent heat of vaporization. You see this latent heat means they want you to find the L. So maybe it's good to start with your, what's the equation again? QML. Q equals to ML. This is the main equation. So give you 2 minutes to try out some calculations. How would you do this question to find L, given all the information in the table above? So if we jump straight into it and say, okay, QML, we need to take a Q, we need to take a M, we need to take a L. But hang on a second. We have two sets of readings though. There's number 1 up here. And there's also number 2 down here. Which one do we use though? Which information? Turns out if you use either, you would get a different L. The L value is different if you use number 1 versus number 2. So how? Turns out, if you thought of means we take average and minus. Actually, why we minus it? Cannot minus leh. There are different values. You use the first set of reading versus second set of reading. So this one is like, oh no, our experiment got problem. Why like that one? Only remember, simultaneous, where does that come from? Remember I mentioned, in all this kind of question, when you use QML MC theta, always assume there is heat loss to environment or heat gain from environment, if they didn't say otherwise. Here they got say, look around and see. No, where? They didn't say no heat loss to environment. No. So we have to assume got heat loss. Oh! Okay, let's do that. How do we do that? All right, let's look at the picture here. So I encourage you, if especially during when you're writing on paper, if you see these experiments, think yourself, okay, this is hot water. Heat is coming out. It's hot. You feel the heat. So this is what we call a heat loss to environment. So our equation have to change a bit leh. So whatever is supplied by our electrical heater will be given to melt not melt, sorry, boil the water, but also some of that will be lost to the environment. This is what we want to use for this scenario only. Each scenario you go and have to think, is it heat loss or heat gain? Okay. I think we can plug in our values maybe. Oh, wait. We need to sub in. So, so maybe we can do here is we convert everything to power. Okay, so I divide all this by time t. So Q over T equals to ml over T plus Q loss over T. Okay, or T, YT, so I can turn into power. So Q over T is also the same thing. Okay, energy over time, heat energy over time. That's power. Power is IV. So I'm going to put here IV of our heater. ml over T, I'm just going to leave it there. And then there is Q loss over T. This will just be called power loss. The rate of energy loss. Power is rate of energy, my energy per time. So this one is what I'm going to use in my equation here to calculate. Okay, yeah. Now we try plug in the values. So the very first one, I'm going to rewrite that here because if not I cannot see it. IV equals to ml over T plus power loss. IV is power of heater. Okay, let's come over here now. Let's see the top. Okay, let's take our first set of reading. Remember when there's two sets, probably you have to do this two equation thing. Let's start with the first one. Number 1, I times V, current times voltage. So I take 5.2, 11.5, I just write it out. 5.2, 11.5 equals to, what is this M? Oh, the mass that become gas. So we lost 5 gram in 300 seconds. So we plug it in. So 5, Miss can keep in gram, can. Why? Because here the unit is in gram. So it's okay lah, we stay in gram, it's fine. Good, I don't want to convert. Kg will be a lot of zeros. So 5 over time 300 times the L. Plus some power loss. I have no idea what the power loss is, but I'm going to write it down first. Then we have our second set of data. We plug in the same thing. You see, we cannot solve there. We got two unknown. We don't know L, we don't know P. So we do it again, but this time for the data set number 2. So we have I times V, 6.4, 14.2 equals to the mass, 9.1, over 300 seconds times L, plus who knows what P loss. So we have two unknown, L and P, but fear not, we also have two equations. So when you have two unknown, two equations, you have to do simultaneous substitution. Do some, that's what maths call simultaneous. So how you want to solve is really up to you. The shortcut that I like to do is just minus both. So, oh, that's what you mean, Alan, minus. I see. Minus two equations. That's right. So we need to do the minus. One way is to take, let's see, what shall I take? Just take any one minus any one. Okay, I just take 1 minus number 2. Equation 1 minus equation 2. Must have enough space here. Wait. So do solve simultaneous. Equation 1 minus equation 2. Means I will take all this minus this one, and then all this minus this one on either side of the equal sign. Okay, let's write out what we have. So this one will be 5.2 times 11.5. That will be 59.8. Minus 6.4 times, is this 14? Yeah, 14.2. This is 90.88. On the other side, this one minus this one. Okay, slowly write. 5 over 300 L minus 9.1 over 300 L. L and L can factorize, huh? We factorize a bit easier. So we take out the L from these two terms. So we have that. Okay, last one. P loss minus P loss. So here we have to assume that in each setting, the rate of energy loss is the same. Because remember, P loss power is rate of energy loss. Same. Why same? Because our water is kind of fixed at 100 Celsius. Environment, we have to assume it is fixed at, I don't know, 60, 26 Celsius. So temperature difference, we assume is always the same. And your container, you didn't change container halfway, you use the same container. So insulation is the same. So rate of energy loss depends on these two, is the same. Cannot halfway suddenly say, hey, can I add some wrapping around the container? Then different already, your experiment. The heat loss is different. We don't do that here. So we do this, we solve, we can find out L, press your calculator a bit. You should get an L value of close to 2274.1. Round off can be about 2, let's round to 2SF, 2300. I'm going to zoom down a bit. Here we go. Okay, so this type of calculation, one is for final, as usual. One is for, where's that equation? This equation, where you have energy conservation, power in, power out, but also power loss on one side. It can be this version or this, where is it? This version also can, where you talk about energy instead of power. Rate of energy. Then if you got either one of these equations set up, okay, you substitute the values, that's okay. This one or this one.